Okay, so while other people are joining, so let's slowly start. Okay, so do you have any question about the two lectures? Some doubts? Everything was clear? Okay. Okay, so just a quick, extremely fast recap. So we have seen now gravitational waves emerge in GR. So what are the main sources, the main detectors, and the main frequency bands where these gravitational waves show up? Okay, so we have seen that in some particular frequency band they appear, they are resolved sources, so they are transient signal that appear in the data stream. Okay, while there is this how to say background signal that more or less is everywhere. Okay, with different behaviors. Okay. And then we have solved the equation of motion for these gravitational waves. We have seen how they propagate in our universe. Okay, so the idea, and we have essentially listed, if you want, we have derived the observable quantities for a stochastic background, that is the gravitational wave spectral energy density, okay, related to the characteristic strain, okay. Okay, this is the first quantity. So you compute this from, let's say, your mode function, your power spectrum, the 2-point function. You relate to this quantity that is one, or the most common quantity that you see in the plot when people describe stochastic background. And then, another quantity related to this is the spectral density of your signal, okay, that is related again to the characteristic strain, so you can essentially translate one in another's, okay. So now you have everything more or less to understand when you see a plot, what is the, let's say, the energy density in gravitational waves that you have in your signal, and you can compare it with the noise of the detectors. So we will see some example today. So as you can see, so up to now I only assume that my gravitational wave background depends only from the frequency, okay? Because the frequency, in principle, is the easiest, if you want, tools to distinguish the source, the origin of the stochastic background, right? So let's see today why the frequency is the most common and, if you want, the easiest one, okay? So what I will do today is essentially focus on the two examples of the two main components of the stochastic background. In the first 15 minutes, I will show you how the predicted shape of the astrophysical background comes from a simple two-body problems. Okay, it's a very how to say simple calculation, but just to give you the feeling of the spectral shape expected from this signal, in the sense that whenever you have a source like that, at least you already know part of the spectrum, so you don't need to go crazy doing numerical integrations. And then in the second part, we will focus on a couple of cosmological sources, if we have time to, okay? And I will connect the primordial power spectrum of these sources with the spectral energy density today, okay? So consider that this guy is observed today, okay? All these are observed today. but these are primordial sources. So we have to find a way to connect our early universe with the measurement today. Okay, so let's start then with the astrophysical background. So I think that in your mind, the idea that when astrophysical sources are perceived as a stochastic background is quite clear, right? So it's easy to imagine. At some point, you have a limited horizon from your, if you want, for your from your gravitational waves detectors. Whatever is beyond, if you want, this horizon, or is below the resolution of your detectors, appears as a stochastic background. So what is a stochastic background for LVK could not be a stochastic background for other better detector, or if you have a network of more detectors, okay? So because of course the resolution is related essentially mainly to the length of the arm in a first approximation, but also is related to the distance when you triangulate more detectors from one detectors to another, okay? This is the rough way to estimate the angular sensitivity of a detector or a network of detectors, okay? But the situation is more complicated than that. And we will see with the Fisher tomorrow, for instance, if you perform a Fisher on some resolved signal, you can have an idea of an idea of the angular resolution performing a statistical analysis, for instance, on the sky coordinates of your gravitational wave source. But so we will discuss it better tomorrow. So now what I want to derive essentially is my spectral energy density, okay, from unresolved astrophysical sources. Okay, and the calculation is extremely easy because there was a guy in the 2000 that wrote a theorem, okay, that wrote a paper that has never been published, okay, but this is a theorem to compute the expected background from astrophysical sources. So it's a wonderful unpublished paper, but is today is the reference paper for computing this signal. So, and the idea, as you will see, is extremely simple. Okay. So, what you have to do? Essentially, the only things that you have to do, you have to integrate all your objects that you see on your light of sight or of your line of sight. Okay. So let's see how to do. Okay. So let me introduce the concept of energy flux. So I don't strictly follow the paper because I simplify many of the calculation, okay? But if you go through this paper, so it's quite easy to follow and to reproduce all the calculation, okay? So I do some, let's say, some simplification, okay? Okay, let me introduce the concept of energy flux. So that is, if you want, the energy that is traveling through some area A over a time t, okay? So this means that I can define my flux as my energy over some area in some time t, okay? So in this lecture, I will put and I will remove a factor of C and G, okay? Just because sometimes it's easier to do the dimensional analysis, sometimes it's not important. So don't complain too much, but you can do it precisely. So if you then just to do divided by C, you have A, T, C. So this is essentially my energy, okay, over the volume, over all the volume of the universe, if you want, okay. So, and this is, as you know, an energy density, because I want to arrive at computing an energy density, okay. So why I compute this? Okay, I compute this because if you remember the definition of my spectral energy density, so we have defined it as 1 over rho c d rho gw over d log f. Okay, let me use this. Okay, so first of all, let me write it without the log. Okay, so this means that this is rho c df over f. Okay, so what I just need to compute, yes, please. Okay, so what you just need to compute is this sum of all the contribution to the variation of the flux in frequency. Okay, so but what is this flux? So if you consider all these sources that are in your line of sight, so essentially is the sum. Okay, so it's an integral from 0 to infinity, okay, over the redshift, okay. It will be clear what is this guy soon, okay, this R of Z, and for people that are less familiar with this quantity, I will explain them soon, okay. The only thing that you have to remember, okay, is that this is the luminosity distance that is telling you more or less the distance at which the object is, okay, at a given redshift, okay. This is the rate of sources that you have, okay. Let me write it, because this is the most important quantity that in some way sets the level of your background, okay. Okay. Okay, no, you don't need it. Okay. Okay. The EGW over the F is the energy spectrum per single source. So evaluated at the source, it will be clear soon. Okay. And yes, these are the quantity that you need. Let's try to physically interpret this formula. Okay, so essentially what you are doing, you are integrated over over all the fluxes or all the energy spectra for all the sources that you have in the sky. Okay, so you consider how many sources you have per unit time. You consider the distance from these sources, and what you add here is a factor that takes into account that your universe evolves. Okay, so whenever you compute something at your source, to translate today, you need to redshift it. Okay, that's the standard way. So yes, the interpretation, I think it's very easy. So nothing complicated. So the rate of sources, this is what I call R. As we will see later, it's very important. So this can be written, if you want, in terms of the comoving rate. Okay. When I add C, this is the comoving one. Okay. okay, for co-moving volume, okay. This is it. So now let's give a bit of definition for this. So what is this co-moving volume? So dV is, so we are talking about a volume. So here there is a cube O times the proper volume, okay? So and this is equal to 1 plus z to the cube 4 pi square dr equal to 1 plus z over 4 pi dl square dr, okay? So remember that the definition that relates the luminosity distance to the proper distance is this, okay? So dr is equal to c over h naught times 1 over, so I neglect the radiation contribution, okay? Okay, this is the dr. Yes. And yes, now I can rewrite my rate as 4 pi dl square over h0 r c z times 1 plus z, and here there is this quantity, okay? So if you do this, here there should be a c, okay? So essentially what you get, what is this? This is the co-moving one, yes. Okay. So if you do this, so essentially what you get is this, okay? And let me write it properly. So if you have done this, now you arrive at the already in 2 steps essentially to the definition of the spectral energy density, that is this, okay? So you plug everything in the initial formula, in that one, and you have yes. I write it in terms of the luminosity distance. There is also, yeah, yes. Okay. Okay, this is again a very easy interpretation. So you are integrating over all the redshift, okay? Your co-moving rate of sources, you redshift it to bring to today. So, and you integrate over all the sources, the energy flux from all the single sources, okay? So when I write S, this Fs is the frequency at the source, okay? while when I write this f is the frequency at the detector here. Okay, so you need to redshift, you need to take into account the redshift. Okay, so now the next step is essentially to evaluate this, because more or less everything from here we know, but what we or we assume some distribution for this, or we have some prior on this. So what we are missing is this. Okay, so we want to know how to compute the variation of the energy density of gravitational waves in frequency, because what we need at the end, we want to know the frequency shape. So the only frequency dependence come from here. Okay, yes. So let's consider the following situation. Let's assume that you have a two-body problem. Okay, so you have two black holes separated by some distance r. Okay, this is m1, this is m2. Okay, this is how this rotates. Here you have this I call r1, this I call r2. Okay, so this goes in this way, this goes in this way. Okay, so this is the case, for instance, of a compact binary system. Okay, so that you can think as a binary black holes or a binary neutron stars. So just to give you some definition that you know, so capital M is the sum of the two masses. Mu is what is called in the community reduced mass, or in the two-body problem if you want. Then I introduce another quantity that is typically used in the gravitational waves community, that is the chirp mass. Okay, that is m1 m2 over m1 plus m2 to some power. Okay, and this is equal to mu to the 5/3 over m to the 2/5. Okay, so these are just definition that you know. Okay, except for the chirp mass. So the trajectory of these two body will follow, as I was saying, the two body problems. So you have these. Okay, R2 is equal to minus m1 over m times r, where this r is r1 minus r2. Okay, so if now you want to compute the total energy of this system, right? So what you then the next step is to compute, sorry, the velocity. Okay, v1, that will be the derivative of r1, so that is equal to m2 over m dot r. Okay, yes, 3 over 5, probably you are right. Yes, oh yes, of course, thanks. And this is equal to minus m2 over m1 r dot 2, that is equal to, I just rewriting this in terms of the ratio of the two masses. Okay, and I relates v2 and v1. Okay, so it's a simple calculation, nothing complicated. So with this, I can compute the total energy now. Okay, so the total energy will be 1 half m1 v1 square plus the sum of the kinetic energy v2 square minus the potential energy. Okay, so let me cancel here. So if you trust in this simple calculation, or if you trust in the two-body problems, okay, so now you can rewrite that one in terms of the reduced mass, okay, as this. So imagine, remember how do you can see a system of two body, okay, R. You can write in this way, okay, where now this V, okay, is the difference between V1 minus V2. Okay. So now I consider the Kepler law, or if you want from Newton's law. So I have that the mass times the radius over the angular velocity is equal to gm over r square. So okay. So I can compute the angular velocity from here or from the Kepler's law, right? So I compute my tangential velocity, okay? So in this way I have that v square is equal to gm over r, okay? So, and I plug this here, okay? So if I plug this here, what I get is minus 1 half g mu m over r, okay? That's the total energy of my system, the orbital energy if you want. So now what is missing? So it's just missing the conservation of energy, okay? So as you know, the variation of energy due to the emission of gravitational waves must be compensated by the variation of the total energy, right? At the end, you just need to equate these two. So if you assume this simple relation, the conservation of energy, so what you have here, you can rewrite this in a different way. So this is dr times dr over dt, okay? So this is mu over r square times r dot, okay? So, and now what you do, you use the Kepler's law. You know that r prime is equal to minus r times the angular velocity, the derivative of angular velocity over the angular velocity. So then you just arrive, if you want. I skip some steps, but they are very trivial. So okay. So you arrive at writing this, the chirp mass to the 5/3, okay, minus 1/3, okay. So you have everything now, okay. So the last step that you miss is write this in terms of frequency. So you have that you plug in the original equation, okay. This is dt over df times de gw over dt, okay, right? I just take these, I do this simple trick, okay? So this means that I have 1 over omega prime times dE gw over dt. I take this, I plug here, and what I get, okay, mc to the 5/3, the chirp mass to the 5/3, times f to the minus 1/3. Okay? Just from here. Yes? You just need, so you know that r goes like to m to 1/3 to the omega to the minus 2/3. You take the derivative of this and you just get that, right? R dot, yeah, but you need to take into account this, right? These are two bodies that are evolving. So what it matters is this frequency dependence, because this is right anyway, so you can do whatever. Also, if you do the proper calculation, and I suggest you to do it, so what you get at the end, okay, is the following thing. The precise, the exact calculation gives you pi to the 2/3, okay, g to the 2/3. So I left away these terms, but you can even get them from dimensional analysis, okay, to f to the minus 1/3. So if you do the exact calculation, this is what you get. Not so different from what I get in 5 steps, okay? So this means, okay, that your omega GW, okay, let me go here, at least in the frequency shape, okay, you have an f from here, and you have an f to the minus 1/3 from there, okay? Forget about the other, because we are focusing on the frequency shape for the moment. So you don't have anything, at least if you consider the two body independent from the environment, you have this. So, and this is telling you that whenever you have two body in spiraling among them, okay, this is valid in the spiral phase, okay? I'm not considering merger and ring down and so on. So your omega for an astrophysical background will always go as f to the 2/3, okay? What this means? So this means, okay, that this gives you a simple tool to understand, so if, for instance, this signal comes from an astrophysical background or something else, okay? So if you do the calculation properly, okay, so is it clear? So of course, we did some assumption here, okay? We assume, first of all, that MC, okay, is the same for all the sources, right? Because I assume that all the sources that I integrate so have the same chirp mass. Of course, this is an assumption. What you need to do, of course, or what okay, let me write more in general, more than the chirp mass, okay? So you have to assume some probability distribution function for the astrophysical parameters, okay? This is, so in this case, I assume that my astrophysical parameters are just, is just the chirp mass, but of course you have the spin that typically, okay, you have many astrophysical parameters on which you should integrate. So if you want to write, for instance, the equation including the dependence on the other parameters, okay? So of course your d over df will be the following: g to the 2/3 over 3 f to the minus 1/3, okay? You, of course, ask, you have some information, for instance, assume that you want to consider as the distribution on the chirp mass or on the masses of the two objects, okay? Yes. Why not? Yes, you should. Yeah, yeah. Yes. So this means that you have to integrate over the distribution of the chip mass. So these are some information that the collaboration is giving us, because it's starting observing uh, a lot of events, 100 of events. So at this stage, we start having some information, for instance, on the distribution of masses for binary black holes. So you know, for instance, that the distribution on the masses uh, given by LIGO Virgo is a power law, okay, plus a Gaussian peak, for instance, okay. So this means that whenever you want to integrate that quantities, so you have to take into account the distribution, the probabilities, the PDF of your parameters. So here I just assume the mass as my parameters, but you have 11 or even 16 in the full case parameters in which you have to integrate. So okay, this is a simple naive calculation. So if you want at the end, okay, so I didn't tell you another key ingredient, that is the merger rate, right? Because the heavily dependence on the redshift, okay? So now I just told you the dependence on the frequency, but there is also dependence on the redshift, because at the end, remember, so we are doing this integral between 0 and infinity, okay, right? So, but we have a distribution that is very important when we consider your stochastic background, okay? So how these events, the rate of events along the redshift, okay? So looking at the data that we have up to now, so the distribution on the redshift given from uh, LIGO Virgo looks like a power law, okay? To some a power law, just like this, okay? And of course you have bounds on these parameters, okay? This is an approximation that is valid at low redshift if you want. So people, when are start thinking to, let's say, extend this at high redshift, they do an assumption, okay? They assume that, okay, let me write it. They assume that the what is called the merger rate, so the merger of events, is proportional to what is called the star formation rate. Okay? So in principle, they assume that the number of mergers, okay, tracks, if you want, the rate of formation of stars. So the rate of formation of stars, we have a fitting formula, okay, we have a fitting formula, yes, by Maddow and Dickinson, okay, that has more or less a shape like this, okay. So in principle, what you are assuming here, assuming that the merger rate of events tracks the star formation rate, is that the merger rate has this typical shape, okay. So this means uh, that it increases, and this is the increasing that you are seeing here at low frequency, okay. Okay, probably it's not well known, but okay. Then it starts increasing and should have its maximum at redshift around 2, okay? And then if it's true that tracks the star formation rate, it starts to decreasing at high redshift. So we would, if this is right, so we would expect that the maximum of events will appear at redshift 2. Okay, this is the expectation for the astrophysical background, but also for resolved sources, of course. So when you do this integral, okay, you have to plug inside this object. Yes. This R of Z. This. This. Yeah. Yes, I put it here because, of course. Yes, that's an important question. Thanks. So this is the way to normalize this merger rate. So what you do, you normalize it at the value that LIGO Virgo have measured, right? So the calibration, the best fit for LIGO Virgo is given at redshift 0.2, okay? So this is the value of the merger rate at redshift 0.2, okay? That if I remember right, is around 28 events per gigaparsec cube per years. Okay, this is more or less probably people that are in LIGO remember better than me. Okay, so this is the way in which you set your normalization, because of course whatever you observe at high redshift, at low redshift, it should match the LIGO Virgo value. Okay. So there is an extra step to do here to connect the star formation rate to the merger rate, okay? Because of course, from the formation of the stars to the merging of the binaries, there is some times that pass, okay? So if you want to do the stuff properly, okay, you should take your star formation rate distribution, okay, and you should multiply from some distribution of the time delay, okay? And you should integrate over the time delay, okay? I don't enter into this detail, but of course, there is some time to expect to pass from the star formation rate to the merger rate, so and you have to integrate over the distribution of the time delay, okay? But it's okay, it's more technical, I don't think that you need. So, final things on the astrophysical side, okay? So, while for astrophysical object, we expect that they have a merger rate that tracks this, at least this, but if you want to go beyond at high redshift, tracks this star formation rate, so it has this shape, okay? So for primordial black holes, okay, that people asked yesterday, you expect something different, okay? So primordial black holes, as you know, as you probably know, so they form when large fluctuation of the energy density of the curvature perturbation re-enter the horizon. So these are essentially over density regions that if they go above some threshold, so they can collapse and they can form these so-called primordial black holes. In principle, what we expect is that if they exist, so they are at very high redshift, okay, this object. So people has tried to numerically simulate the merger rate for this object, okay. I take it from the literature, but I don't. So the paper is from Rydal. Okay, I forgot to put the number of the references. If you want, you are interested. There is one estimation of the merger rate for this object. Okay, and this is the expectation for the merger rate of primordial black holes. This is one of the most used, let's say, merger rate fit for primordial black holes. So if you just want to have a comparison, so while we have seen that these are 0.2, so as a distribution like this, okay, where here you have, okay, let me write here, you have 10 to the 1, 10 to minus 10 to 0, 10 to minus 1, and 10 to minus 2. Okay. So for the merger rate, depending on this value that is model dependent, okay, for the merger rate for different value of epsilon, this is epsilon 1, this is epsilon 0.1, okay. For different value of epsilon, you expect different behavior of the merger rate, okay. Here, so you expect that this merger rate instead of decreasing, okay, this is R of Z, it increase and then it reach a plateau. So here you should have 2. This is the redshift, okay. This is 4. This is 0, okay. So you expect that with the LVK at the level of observability, we are here. So with advanced version that are called A plus detectors, there are some advanced version of LIGO. We expect to be here. So, and with the ET and LISA, we expect to be around here, 8. So, and this tells you why, for instance, these third generation detectors that I discussed the first day, like LISA and ET, some space-based interferometers or third generation ground-based interferometers becomes very important to understand, to probe the existence of these primordial black holes, right? So because if you go above, it's model dependent, of course, but if you go above redshift 3, okay, and even more, so you expect that you can distinguish these you can find some primordial black holes. People have also computed, okay, that's very important because you ask me. So what is the expected, now that we have the frequency shape, so what is the expected signal in our detectors, okay? So assume that we are in the LIGO band, okay, 10 and 10 to the 3 frequency, okay? This is 10 to minus 9, okay? So this is the sensitivity curves of LIGO 05, okay? So next upgrade of LIGO, okay? So if you trust in my calculation, okay, we expect that my astrophysical background will appear in the advanced LIGO if the constraint that we have now does not change much on the merger rate. So the signal will show up in the LIGO 05, okay? This is the f to the 2/3 shape on omega, okay? So if you compute the expected background, I'm talking about the background from primordial black holes, okay? So this is the expected signal that we should have in LIGO 05. This is stellar origin black hole, and this is our PBH signal. So you see that the signal from PBH, the astrophysical signal from PBH, is quite subdominant, okay? So, but instead we expect to measure the astrophysical background. And of course, if we will improve with ET, for instance, of 1 order of magnitude, the situation will be even better, okay? So now probably I exaggerated a bit, but more or less we are in this situation. But what I want to stress is that this phase, the spiral phase, this is all signal integrated over the spiral part, so is a simple power law, okay? And then you have this behavior, this part, where it starts to matter what is the merger part of the binary. So you know the binary spiral and then merge. The merger part mainly influence this part of the spectrum, okay? And why this part is analytically under control? managing this part is more complicated, and you need to go numerically as mainly. Okay. So if you don't have any question, okay, this is concludes the part on the astrophysical background. Okay, let's now move to the cosmological one. Okay. It was done to eat then the second part. Okay, when the source that contributes to the background, the main contribution to the stochastic background, for instance, in LISA, okay, is the one coming from these spirals, the one that is guaranteed that is there. Okay. Of course, you have to sum all the signal. You have to sum the spiral part, the merger part, and also the last part, of course. Right? The one that we have under control analytically is the spiral part, right? So whenever you have two supermassive black holes, or better, whenever you have a distribution of supermassive black holes, stellar origin black holes, massive black holes, that they spiral, and they are in many, they will always go as to f to the 2/3. So this is the long discussion that is now in the PTA community. Why? So for the supermassive black holes, we expect something like this, but then the, if you want to fit good the data, so there should be at some point a tilt in the spectrum. Okay, this is in omega. Okay, don't be confused between omega and h. The spectrum tilts a bit. So in this part, even if it looks in the okay, there are some environment effect, some astrophysics that is not under control, that impact the emission of the signal, and so impact on the shape of the signal. Okay, but as long as you are in the spiral and you don't take into account strong environmental effects, so the signal is a simple power law. Okay, for every object that, even for the bottle that rotates around you. Okay, so let's go to the cosmological case. It's more under control for me. Okay, I mainly work on the cosmological sources, even if there is a lot of cosmology also in the astrophysical sources, because I didn't tell you that, for instance, so here we assume that the Hubble parameter is given, but in principle, you could also combine the astrophysical signal and the resolved signal to put constraint on the Hubble parameters, for instance. And the advantage, probably this I should stress, the advantage of the astrophysical background is that while, so with the astrophysical sources you are close, okay? With the astrophysical background you are integrated from redshift, let's say 8, up to redshift 0, okay, right? So you have all the information at the redshift. That means having information on the population properties, okay? Some things that to have the same accuracy from resolved sources on the population, it's a bit, it's quite hard, okay? Okay, let's go to the Cosmos source. So I was planning to derive the solution of the equation of motion, but since it's late, I will give you directly. Then I will put in the notes that will be online at some point. Okay. So this will be the okay. So okay. So let's go back in the cosmological setup. Now we are very close. Let's go in the early universe. Okay. So let's write my metric. Okay. My Friedman-Robertson-Walker metric. Okay. With my tensor perturbation that you now know what is it and how many degrees of freedom it has. Okay. Okay, so if you take the Einstein-Hilbert action, let's take this other approach today. So, okay, sorry. You perturb this Einstein-Hilbert at second order. You keep just the tensors. This is the perturbed second order Einstein-Hilbert, okay? So you derive the equation of motion that we is the same as yesterday, okay? So, and you solve it, okay? But you solve it in on super horizon scale. In a quasi de Sitter universe, okay? So you will find the full derivation in the notes, okay? So you will find that the solution of your equation of motion, I've read the full solution, okay, is this one, I epsilon I pi 2 epsilon 2 over epsilon, okay? So it comes from okay, don't be scared. So this is the Slaughter parameters, that is minus h dot over h square, okay? Are the gamma Euler function. So this solution is this solution, if I remember well, so it comes from solving this general second order differential equation. So it is the solution will be Henkel functions, okay? So when you expand the Henkel function on super horizon scales, okay, down that you remember, so okay, k much smaller than h, okay, you get this solution, and these are some Euler gamma function, okay, and you should have everything. What matters is this part, okay. I will set now epsilon to 0 or even epsilon very small, as you know, in quasi de Sitter, okay. So then the solution becomes I write it like I h over mass Planck times k cube, okay. So this is the solution, okay. So now you can compute you take yes, and you can also put this k over a h to minus epsilon, okay. So you just do this approximation. So now you can compute the power spectrum, okay, because as I told you yesterday, the observable quantities for primordial universe, so is the power spectrum. So the power spectrum of H, okay, of K, so that if you want is H of K 1, H of K2 star, okay. So the power spectrum is the Fourier transform of the 2-point function, okay. So there are some factors here, 2 pi cube delta 3 d of K1 minus K2, okay. So if you compute the power spectrum, that in this simple case, if you want, is just hk square, okay? So you arrive at at this form, okay? 2 over pi square mass Planck square. Okay, let's write it this way. Okay, right? So I just uh, square this, okay? HH star. So if you remember, so this was something that I told you in the first lecture, why it's important to measure primordial gravitational waves. So essentially, this is telling me the energy density at which inflation happens, okay? But what I realize is that also, very important, is that this uh, power spectrum has a so-called spectral tilt, okay? Till okay, that is equal to minus 2 epsilon, okay? Remember that epsilon, to have inflation, okay, must be very small, okay? And typically, so you need of order 10 to minus 2, okay? So this means that if you compute this power spectrum, okay, it will have a, what is called slightly tilted red spectrum, okay? This means that more you go on smaller scale, more your power decrease, okay? And this is something that is valid in single field slow roll inflation, okay? This is something that you have seen for sure in your classes, okay? So if you compute the tensor power spectrum, it will have a behavior like that, okay? So, but here, as you remember yesterday, okay, let me just sketch a bit this. So here we are we are computing an inflationary, let's say, observables. Okay. So as you know, here I have A, here I have the comoving wavelength. So I take a modes of wavelength of wave vector k that is related to lambda. So I compute the power spectrum on super horizon scale. Okay. When the solution, you know how it behaves, okay? But at this solution, okay, here is frozen, but at some point, here is the end of inflation, okay? Here we enter in the radiation-dominated phase for standard evolution. Here we have the equivalence, okay? Let me call it a star. And here you have the matter domination. And here is today, okay? So these modes, this means that you have computed your power spectrum here, right? Here is the typical way where the typical time at which you compute the power spectrum on super horizon scale, but then you want to measure today, right? So, but this means that we are still uh, uh, we are still looking how to connect these two here, right? Because these modes propagates uh, during radiation domination and also during matter. So the situation for the CMB is a bit different because you know you compute the power spectrum, then these guys arrive at the CMB, arrive here if you want, in a brute force, and then you measure photons, right? Instead, here the gravitational waves propagates and we measure them today, right? Because you know, important point, when you measure gravitational waves on the CMB, it's an indirect way to measure gravitational wave because it's the impact of the gravitational waves on the CMB photons. When you measure the gravitational waves with interferometers, you are directly measuring the gravitons, right? So this is the subtleties. That is an indirect effect. This is a direct effect. So that's the reason why we distinguish the two. So this means that the formula that I give you is partially correct, okay? The solution that I give you is partially correct because the correct one will be something like this. It will be clear in a moment. It will be my tensor modes today, okay, will be what is called the transfer function that depends on time and on k, okay, times my super horizon solution, okay? So you need to attach to your super horizon solution some things that tells the evolution in time of your modes and takes into account that your gravitational waves can re-enter in the horizon or in radiation domination or in matters, and then also there is the dark energy era that here I didn't consider, but you have to take into account everything, all right? So if you uh, consider interferometers, okay, the typical gravitational waves that appears at the interferometers re-enters the horizon in radiation domination. So this means that is all the modes essentially between these and these, okay? All the modes that these and these, because here are all the modes that re-enter in the horizon in radiation domination. Yes. Sorry, yes, yes. When you add the transfer function, you need to rescale at the end with the growth factor that you have still in the transfer function. So you need to take into account still in the transfer function. When you use Yes, when you use the full ones, it takes into account everything. Okay. Sorry, it's exactly the same thing. Yes, yes, it's exactly that. You should to take into account the full evolution. So this means that gravitational waves interferometers, so typically, but not only, see gravitational waves that enters in radiation domination. So if you want to understand better this sentence, you have to connect the frequency of your gravitational waves detectors with the scales, okay? And you will see that they correspond. So since we are looking essentially from 10 to minus 11 Hertz up to 1000 of Hertz, okay, right? These are all gravitational waves that enters in radiation domination, right? But it will be clear when I will do the full picture. So the transfer function in radiation domination, okay, what is I call typically people call tau or big tau. I call it chi. It's the same thing. Okay, is a J spherical Bessel function of k tau J0. This is a spherical Bessel of order 0. Okay, that is essentially a sign of k tau over k tau. Okay. Of course, it can happen that there are gravitational waves that enters also in matter. Okay. These have a slightly more complicated. Uh, okay, it's 3. A slightly more complicated form. Instead of a J0 is a J1. Okay. So remember that is still a spherical Bessel function. So now we have everything, okay? So then we can compute my my omega today, okay? Let's compute it. So if you now remember that this rho GW is equal to mass Planck square over 4a square. Okay, I wrote in terms of mass Planck square, so you know how to translate the two. Okay. Okay. So now, right? Because now I have to consider also the transfer function. Remember that now all the time dependence is inside here. So when I take the prime derivative is only in the transfer function. That's the nice stuff of the transfer function, that it keeps all the information the time evolution. So you take your derivative, okay? So this means that you have 1 over 32 pi g a square right? So that's this is the power spectrum, right? This is the square of the transfer function, and this is the usual prefactor, right? Okay. So the calculation that you did in the exercise is similar to what we do here, right? So the time derivative of my transfer function inside the horizon, because remember that now we are observing, we are inside the horizon, fortunately, okay? So is k over times chi, okay, sorry, is k times the transfer function, okay, inside the horizon, right? So this means that now I can finally compute my omega, because I have everything, I have rho, right? So if I compute omega, and let me stress today, okay? Because now we have included the transfer function. Okay? This will be k square over 12, 80 square, because now I have to evaluate the scale factor today, h0 square, chi of tau square, ph of k. Okay? Bravi, yes. This you can set to 1 if you want. And this is a normalization that you can do, okay? And this is the easiest, let's say, derivation of the transfer function. So if you want to have the full transfer function, the one that you can derive considering all the epochs, okay? I just derive here, I just consider generically a simple case without considering that when this gravitational waves propagates, there are many effects like decoupling of relativistic particles, okay, that you have to take into account because it's an energy density as well. So the average transfer function, let's say the full one, is something like omega rad omega radiation over square root of 2 G star over K times G star of 0 to 1 half G star 0 of S G star of K S times K0 over K times 9 over 16 K equivalence over square root of 2K to the 2 plus 1. Okay, if you want the full transfer function, is this one. Okay, here, here, below square root of 2. Whenever you don't know something, there's always a square root of 2. And what are these guys here? Okay, so this counts, takes into account the number of extra relativistic degrees of freedom that change during the evolution of the universe, right? So G star is the number of relativistic degrees of freedom, right? And you have to take into account this because this is an energy density, so you have to sum everything. So if you, for instance, consider just the simplest case of neutrinos, okay? So the neutrinos has an impact on the gravitational waves that, for instance, just neutrino reduce the amplitudes of the gravitational wave signal of the 40%, okay? This is the so-called Weinberg effect that he computed first, okay? So now we have everything. Let's compute the signal today, right? And let's see where is it. Okay. So let me take that. Let me do a bit of simplification. Okay. So I can compute my omega bar. So remember that it's an average quantity. This goes like omega radiation. If you put all the stuff together, and you put all the numbers there, okay, over 24, simply so simple, times pH of K, right? Of F or of K. Let's write in terms of, yes, it's better in terms of K. The two are related. So this is essentially a simplified fast estimation of the transfer function, okay, right? And this is my primordial power spectrum. Let's now give an order of magnitude, okay, considering the bound that we have, because you remember this, we have bounds from the CMB, right? So on these, we know, for instance, that this is the most recent bound on R, okay, that is equal to pH over p zeta. This must be smaller than 0.03, right? So what I can do, I can rewrite my equation like this in terms of R times p zeta, right? I just substitute pH as times R p zeta, okay? So these guys, so is of order 10 to minus 5, right? These guys is of order 10 to minus 2, and this guys is of order 10 to minus 9, as you know, from CMB observation, right? So this means that my omega GW from single field inflation, slow roll, okay, the situation where we put, is something like 10 to minus 16 R over 0.03. I just do this normalization, okay? This means that this is the typical expected value, so evaluated at some pivot scale, but this is the typical expected value from single field inflation. Now let's see where is the signal when we compare it with the gravitational waves interferometers. Okay, So in the first lecture, I give you more or less an order of magnitude of the different detectors, okay, of the noise of different detectors. Now let's put this noise, if you want, in omega units. You know how to do it. Here is omega GW, okay? And let me introduce one quantity that it will be very important. That is the power law sensitivity, okay? It will be clear in a moment, okay? And this is one of the exercise versus frequency, okay? So if you write, okay, here is 10 to minus 19 as usual, 10 to minus 18. Here it's 10 to the 4, 10 to minus 5, let's write here, 10 to minus 10, okay, 10 to minus 16, okay, and 10 to minus 18. So we have seen that CMB experiment, they are they work in this frequency regime, okay? So I didn't put still anything on the y-axis. So Lisa will work in the millihertz regime, okay? While ET will work a bit less here, okay? Let me write ET, Lisa, CMB. This is Lightbird, for instance. These are the noise of the detectors, okay, in a rough way, in omega units. Keep it for now. So now here I have 10 to minus 12. No, sorry. Here I have 10 to minus 12. Okay. Here I have 10 to minus 14, 10 to minus 16. Okay. Here I have 10 to minus 8. So we have seen that in single field inflation, okay, this omega is of order 10 to minus 16, right? It's really at the border of CMB experiment. The behavior here is like this in frequency. Then you have this slightly red tilted spectrum that decrease, right? With the tilt that is going as minus 2 epsilon, okay? So, and this epsilon is 10 to minus 2. So as you can see, the signal from inflation from single field, the first example that I mentioned you when I talk about sources, cosmological sources, is well below the sensitivity of any gravitational waves detectors, right? At least accepted and planned to be launched, okay? So this means that it's very hard to detect signal, gravitational wave stochastic background from a single field model of inflation, okay? And then, right, you need more advanced detectors that go down here, okay? Like for instance, this was the BBO, okay? Or you can ask yourself, then why people hire these guys to study cosmological background? Because you cannot see it, right? Then the answer is the following. So as I will explain you now, so this is just one model of inflation. It's true that Planck gave strong constraint on single field model of inflation, okay? On these scales, right? Whatever Planck tell you with good approximation is on CMB scales, okay? But we are on different set of scales. So here, remember that you have PTA and you have other stuff and so on and so forth. At the end, I will show on the blackboard a full picture of this, okay? So the main message here is that vacuum tensor fluctuation, so gravitational waves, are not detectable by, let me focus on Lisa and ET, okay? When I means vacuum, I means the standard tensor fluctuation of the metric, okay? And are not detectable because, you know, this is the signal and this is the noise of your detector. You are order of magnitudes below the sensitivity of these detectors. But now let's see why it's important to study the cosmological background, okay? So let's consider one simple extension or two simple extensions of single field inflation. I'll keep it because I will overplot something at the, yes, please. This way. So you see that you are very focused on the top. All the modes that we consider here, okay, these essentially are the modes that re-enter the horizon in radiation domination. So you have to think in the opposite way, where from that plot to this plot, these are the modes here. So my picture is not the best, as you can see. These are the modes that re-enter in matter domination. So simply, let's look at the transfer function, okay? What is, and you compare K with K equivalence, okay? So when K is much smaller than K equivalence, okay? That means that you are in matter domination. So what dominates is 1 over K square. This is 1 over K square, right? When you are in the case of radiation domination, where K is much larger, the first term is negligible, and omega is constant, essentially. It's slightly constant. It's this phase, right? So this is the behavior. So it's always a matter of in which phase of the, this is a translation of that, nothing more. So let me tell you a simple explanation that comes out from a simple extension of single field inflation, okay? That is axion inflation. So if I have time, I want to also discuss, so I have 15 minutes, right? I want also discuss what are the scalar induced gravitational waves, or at least I will draw on the blackboard if I don't succeed to do the calculation. But let's focus for the moment on the axion inflation. So as you know, so when we talk about inflation, we assume that our potential is very flat, right? So your inflaton moves along this potential that is quite flat. This reflects on the Slorol parameters, right? So this means that is completely safe, if you want, to assume that I have a kind of shift symmetry for my field, right? So I'm on a flat potential, whatever rescaling I do, so I don't change much. Okay, so this means that my potential, if you want, is if you want invariant under some translation. Okay. This is the typical symmetry that is respected by axion fields, okay? Axion-like, let me write like. So I don't enter in the details of these, but you know, these are affected by radiative correction, the string inspire axion models. So in order to keep under control this radiative correction, you need to impose this shift symmetry, right? So we translate this shift symmetry for the radiative correction in this way, okay? So one typical potential that you have for this axion-like field is this, okay? okay? And this is not, I'm not talking about QCD action. This is a general particles that the only properties that it has is is a pseudoscalar field. So it goes under a parity transformation, it goes from phi in minus phi, okay? Nothing more. So if you want, there are also extensions considering QCD action and so on and so forth. So to start doing the computation, I need to give you the Lagrangian for this guy, okay? Right? So this is the axion decay constant. This is my axion field, that is a pseudoscalar. This F mu nu is the field strength. And this is the dual. Okay? So the first time that has been studied this model was in an inflationary context was 2011, Cook and Sorbo. This is the archive number, so you can look there for more details, okay? This is your general Lagrangian, okay? So I can decompose my gauge field, my A field, okay? Again, assuming two polarization, okay? Is the similar decomposition that you have for, okay? A lambda of k, A lambda of k tau, A to the A k x plus, okay, should be, okay? So you do decompose the your gauge field, okay, and you move in Fourier space, okay. So if you move in Fourier space, okay, the equation of motion for this axion field is the following, right? This is the equation of motion for the axion. So two important things. So you have two polarization. You have two different behaviors for the A plus and A cross solution, right? That's a peculiar feature of this model. So if you solve this equation of motion, so if you solve this equation of motion, you will see that the only solution that is amplified is one of the two, okay? While A plus, one polarization, is amplified, A minus is not amplified. I wrote crossed, no, minus, okay. Okay, and this goes like 1 over 2k, okay, square root, over k times 2 psi AH. You don't know what is psi at the moment. Okay, where this psi is essentially the velocity of your axion field, okay, to FH, okay. So this means that this axion is going in a tachyonic instability, right? And there's this exponential increasing amplification, right? And this happens only for the A, one of the two polarization. This A minus is not amplified. right? But now we are looking for the tensor, right? So we want to solve for the tensors. What happens here? Yesterday, so there was a questions about yes, please. Here, this is the conformal time. I think so. I think so. It's the first one. Yes, it should be minus plus. Yes. Yes, right? Yes, thanks. Yes. Okay, one of the two is amplified. So we are looking for the gravitational waves, right? So if you compute the equation of motion in the sitter for the gravitational waves, so you include the tensor part, okay? This is the equation of motion for my usual gravitational waves. But now, so to the Einstein-Hilbert action, you have to add this Lagrangian, right? So, and if you do the computation properly, so you realize that on the right-hand side, it will appear a source term. So you compute your energy momentum tensor for this action. So let me write in terms of the reduced Planck mass, okay? And here you have your, let me write it as lambda. I don't remember usually, okay? Your projector tensor that you need to put to extract the TT part of the energy momentum tensor. And here you will have epsilon L, epsilon M, sorry, E, the electric field plus the magnetic field, okay? Where this electric and magnetic field, they are related, of course, to the field A, okay? Okay? Nice. So you have your vacuum tensor fluctuation that are sourced by the axion, right? Very nice. So this means that now you solve your equation of motion for H, okay? So you know how to solve it. You use the Green function method, right? So you first solve the homogeneous equation, and then you add the non-homogeneous part, okay? So if you solve your equation, you will arrive to a solution for your H, okay, right? That now we'll have you will have two solution. You compute your H, and then you compute your power spectrum of H, okay? It will have two contributions. One is coming from what we call the vacuum contribution, the one that we compute above, right? Plus, you have a source contribution, sourced, given by this, okay? Now you have two contributions. You have the vacuum to the power spectrum plus the source contribution, right? In a natural extension of single field. So this, the vacuum one, you know already how much is it, right? We did it before, right? The source contribution is very funny because the fact that one of the modes is amplified and the other is not amplified, it means that the P plus is different from the P cross power spectrum, right? If you then need to specify on which polarization you are computed it, right? So, and if you compute the power spectrum of plus, let me call it sourced, okay? This will be something like 10 to minus 8, h to the 4, mass Planck to the 4, e to the 4 pi xi, over xi to the 6, okay? Sorry. While the p minus, or p cross if you want, sourced, okay, is 10 to minus 10. Look that they are different, while before, okay, p plus and p minus and p plus, they are different, right? So minus to identify that it comes from the yes, the minus one, okay? So, but now you see that you have two contributions. So let's go back. The full power spectrum is the sum of the two. So let's go back here, okay? So this means that you have the vacuum contribution, right? That is always the standard one. When this axion starts to put power, okay, in your source, the power spectrum gets amplified, right? And this is the source contribution, if you want, in terms of omega. And the power spectrum for a simple extension of single field model of inflation becomes visible with interferometers, right? What this means? This means that if it happens that we have a model that is beyond single field, okay? So with gravitational waves interferometers that in principle were designed to detect resolved sources next to your door, okay? So you can open a windows on the early universe, right? This is a completely full primordial model, primordial universe model, right? So in principle, if you want, you can set bounds on psi, right? On the velocity of your field. You can set bounds on the axion decay constant, right? In a completely, if you want, what I say to everybody is that in a completely for free setup, you have designed the detectors to study astrophysics for free. You can open a windows on the a window on the early universe, right? Just detecting, but also non-detecting this signal, because if you are not lucky and your signal is here, is just below your noise of your detector, you are still putting some bound on this quantity, right? For which at the moment, the only bound that we have only comes from here, from the CMB, right? So this is a very simple model. So when a model has a behavior like this, is called blue tilt model, okay? Where it means that NT is bigger than 0, okay? This is a blue tilt model of inflation. So just to conclude, I still, yes, sure. Yeah. No, 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 it doesn't. No, at the end, no, sorry, this probably confused you. So at the end, what you sum here, this is P plus plus P cross, right? But of course, this is 10 to minus 8 compared to 10 to minus 8 and 10. So you just keep the, no, no, the P source is everything. You raise a good point. If you would measure a signal that has an omega, let me call it cross, and omega plus, that they are different, right? This is an indication of the parity violation. So this would be a model that, for instance, could, if we measure something like this, explain a cosmological scenarios. That's very interesting point. So I didn't go in details because you can get confused. At the end of the day, always, what you measure is omega, is P, that is the sum of the two polarization, P plus plus P cross, right? It's not easy to disentangle the two. I would need a full lecture to explain this. So you measure always the sum of the two polarization. But if you have a particular setup, okay, of your detectors, you can even distinguish between the two. Even better, you can distinguish between left and right, because I told you that the right basis to distinguish the chirality is the left-right basis. If you measure something like this, it could be an indication of the presence, again, another peculiar features of the early universe. So I just still 5 minutes from your coffee break, okay? So just to tell you something that is that you can complain about, because you can say, okay, you are very smart, you cook a model, okay, and it works. So it's true, of course. So all what I told you is model dependent. That's the starting point. But there is another interesting things that comes very naturally in GR. Okay. So when we computed the equation of motion for my tensor field, okay, we solve these and we put equal to proportional to T bu nu. Okay, if you want, right? So this is what happens at first order, okay? If you do the computation at second order, and you are very brave, okay? This is the same thing that happens also at second order. The same equation is true also at second order. Forget for the moment gauge stuff and so on. So it happens also at second order. If you do the computation in GR, right? You don't have to do anything complicated, right? So what you get is that H, let me write second here, even if it's not important. It's H second plus, is just to give you a feeling. So you will find that your source term, the right hand side, is proportional to the Bardeen potential square, right? If you do this computation at second order, this is square, it's not second. This is first order square, okay? So you will, again, for free, find that gravitational waves at second order are sourced by scalar fluctuation. So this is something realized in the 70s by Tomita, okay? It was a Japanese guy. And in the 90s by Sabino Matarese, right? This was they were the first two computation on this. So naturally in GR you have this, okay? Then other people work a lot on this. They worked from the 90s up to 2000 a lot. There was a paper by David Wons. Then there was a paper by Daniel Baumann on this that did a pedagogical computation of this, okay? Then it happens that recently they become very hot again in the last 6-7 years due to the LIGO detection. So, but let's see one single thing about this, right? So if you do all the computation, okay, so you will find, okay, it's long, you will find, let me give you just a naive understanding of this, okay? So if you are on CMB scales, okay, these guys, phi, is proportional to the curvature perturbation that is of order 10 to minus 5, right? So we know that on CMB, so we have constraint on the scalar perturbation, on the tensor perturbation, right? And this guy is of order 10 to minus 5. So then you can say, okay, but this guy then it's very small, because if this is 10 to minus 5, my HC that very, very roughly is omega r times phi, right? This is 10 to minus 5, this is 10 to minus 5, this is 10 to minus 10 or 9, okay? This means that my omega, GW, that is proportional, now you know, to pH, okay? It's equal to 10 to minus 2 omega rad times hc square, or the power spectrum, right? This comes from epsilon, if you want, okay? If you do this computation, okay, at second order, so at this gives something like 10 to minus 25, right? Okay, then you say, here you are at 10 to minus 16. So if you go at 10 to minus 25, the situation is much worse than that, right? But what happens? The situation is very beautiful, because if you draw a plot of the scalar power spectrum to the scales, you have strong bound from the CMB, right? The CMB put this strong bound, okay? Then you have strong bound on the matter power spectrum from LSS, okay, right? So assume that here you are in the CMBs, you are one inverse megaparsec. Here you have 10 to the 5 inverse megaparsec, okay? And here you have some bound from the non-observation of the PBH, of the primordial black holes, right? Because still this comes from scalar fluctuation. So this means that if I look at my power spectrum, it's very bounded here, right? And I have very strong bounds that I cannot evade at CMB scales, right? So here I still have strong bounds from LSS, so my amplitudes of the power spectrum is quite bounded. But if I move to smaller scale, large K, so my power spectrum is free to increase, right? So I don't have any bound here. So the only bounds that I should respect is the PBH, not PhD bound, okay? Is the PBH bound, okay? So in principle, I can have a Gaussian power spectrum, right? At some scales, K star. And I can nobody complain if I take this power spectrum at order 10 to minus 2, right? On the peak, right? So now let's go back and let's do that calculation again. So you have, you assume this, that phi is of order 10 to minus 2, the power spectrum, right? H square will go as P R square. R is the curvature perturbation. Means that this is 10 to minus 8, right? Rough calculation. So if h square is 10 to minus 8, you go and compute omega GW again. Now you have 10 to minus 7 times 10 to minus 8, right? That is 10 to minus 15, right? So I am quite close, okay, to this limit here, right? The point is that I can even play a bit with the amplitudes. I can play a bit also with the sigma of my signal. And I can play a bit also on something that is a bit more complicated, on the non-Gaussianities from this signal. So I have region bounded, but I have region in the parameter space where my signal, okay, increase, okay. Just to give you, sorry if I'm late. So if you do all the computation, so you have to take into account many things, also the transfer function and so on and so forth, okay? So there is a increasing factor when you compute the transfer function. You arrive in the situation where this signal can increase, okay? And can even become visible with gravitational waves interferometers, right? You have to push the amplitudes of your scalar power spectrum on some scales where you can, right? You don't have any bounds, you have these bounds, but you respect it. You should be careful with the width, because, okay, I draw it bad, but this goes here, so you cannot have a width large as you want, right? But in principle, and you have to choose one form for the scalar power spectrum that, for instance, you can choose as a delta-like, if you want, to some power of k star. But in principle, okay, in GR, so I have realized that there is a way to push my gravitation cosmological signal at scales here, or if I move my peak even here, of my gravitational signal above the sensitivity of my detectors, right? I conclude saying that while all the models that we study when we talk about extension of inflation, phase transition, cosmological defects, and so on and so forth, they are very model dependent, right? So this is a contribution that besides this amplification of the power spectrum is there, right? So this, my original computation of this is there, right? So we just need the sensitivity. But this contribution is the only one that we are for sure that it exists, because we measure the scalar power spectrum from the CMB. We have seen that with good accuracy it is scale invariant, right? Unfortunately. Uh, and this contribution is there, right? And it's, I cannot claim that it's 100% model independent, because you still have to put it a scalar power spectrum, but it's something that for sure we know that it exists. So yes, the plan was to do the full computation of also of this second model. So it is long. You can do for the exercise that we give you. So, but if you have question, I'm happy to reply to you. Let's stop.